It's about half a minute or so. Yeah, if you go to YouTube, go to Mr. Stapleton, Mr. Stapleton, you should see this going. So, page 6. We're just going to do just enough so that you'll be able to understand the homework and the Newton sled activity, which I'll tell you about in a little while. Okay, Newton's third law. I'm going to see if I can trick you like I tricked last class. I'm going to start with every. Can anybody guess what comes next? Ah, good job. So normally people say for every action there's an equal and opposite reaction. And when is it going? And I used to do it that way. All right, turn that volume off. That's going to be very strange. So I used to do it that way, and then we would think it confused people because what really is important is that every force has an equal and opposite force. Now, I'm going to come back to that in just a second. Has an equal and opposite force. So if you imagine a gun, for example, guns are easy things to think about. I don't spend a lot of time drawing guns, so I'm not very good at it. If I spent a lot of time drawing guns, that would be concerning. So you've got a gun here, and it shoots a bullet, right? So the bullet goes out like this, and what happens to the gun? It goes the other way. And you might think what the bullet does and what the gun does, do those seem equal and opposite? Not really, because if they were, then you'd be shooting your holes in your shoulder every time you shot a gun. So the gun kicks back a little bit, and the bullet moves out really fast and destructively. So what is equal and opposite here? The net force. And remember, net force, I can have the same net force, and if I have a little tiny mass like a bullet versus a really big mass like a gun, what's that gonna do? It's gonna change the acceleration. So you can have a big acceleration for a bullet, and you have a tiny acceleration for the gun. But the force is the same. So it's every force has an equal and opposite force. And I inherited some of this from Mr. Pennington and haven't changed it, so I have to look up exactly what he intends here. It says forces always occur in pairs. That's true. Was this the class where I challenged you to imagine a force by itself? Okay, well, I don't know if we should spend time on it, but try to think of a situation where you could have just one force. You could exert a force on something without it exerting a force back. Can anybody think of one while I'm trying to find what page I'm on? What's that? Wind? So what do you mean? If the wind blows? So let's say there's somebody there, and so the hair is being blown back by the wind. So you're saying the force of the wind on the hair is a force all by itself with no opposite force? Is that what we're thinking? Was that the idea?
No, I was saying it hits your hair, so it's like a force like pushing your hair.
Okay, so the wind pushes your hair.
So I was like, no, I was saying like your mom is wrong.
Okay, yeah, because if the wind pushes your hair, then what happens? The hair pushes the wind. And this wind, if it's going 5 miles per hour and it runs through a whole forest of hair, for example, it's not going to make it through going 5 miles per hour on the other side. It's going to get slowed down by all that hair, that forest of hair. So there's no way to have one force without another force. If you imagine just being out in space and trying to punch the vacuum of space, can you exert a force on the vacuum of space? Not really, because you can't. If F equals ma and there's no mass out there, then first you can't accelerate nothingness. But even if you could, if it had no mass, then you'd get no force. You just can't have a force by itself. Nirmal? If you blow wind, okay, so here's your mouth, and you blow some air out of your mouth really, really, really fast, what's going to happen to your head? It's going to get knocked back. Yeah. There's a video of me at the rink with a leaf blower, and I'm sitting on a hovercraft on the ice of the rink, and I've got a leaf blower pointing this way, and I start accelerating the other way. So you can't do it. It's undoable. So I was trying to remember what he wants here. It says forces always occur in pairs. One body cannot exert a force on another without, and the reason I couldn't figure this out is there's way too much in this space, without experiencing the same force. So you can't exert a force on something else without feeling that same force. You can't pull something without it pulling you the other way. You can't push something without it pushing you the other way. And this is sometimes referred to as action, reaction, which is a little iffy. We're not going to go to the online textbook, but this comes from the online textbook that we never use. Cam?
Does every pull factor be a push based off of a different direction?
Right. Well, I don't know. If you think of gravitational pull, I don't feel like that's a push. But was
That's pushing
what?
them in the direction of the center of the gravity.
So are you saying if there's a planet here and a moon out here, that this gravity is getting behind it and pushing it in? And gravity over here is pushing that in?
That's why I was saying direction is only based off of direction and like actual like areas.
So you have a really good point.
Arrow is a push, right?
Well, so these are being forced together, and they could be being pushed together. If you had somebody back here, some space person pushing that in, and somebody over here pushing it in, and you could also have something here that's pulling on both of them. So that in physics, it doesn't really matter for solving problems. It's only just to I don't know, I guess, flesh out the problems and let us picture them better. So it doesn't matter whether they're pushes or pulls. We're going to get into tension today, and tension is usually a pull, and normal force is a push. Okay, so the swimmer, but I just want to come back to, remember when I was hanging on the door? Was I pulling or pushing the door there? I think you could make a good argument I was doing either, because my hand was here and I was over here. And was I pulling down on the top of the door, or was I pushing down on the top of the door? I don't know. I mean, I was kind of pulling my body up, but I was pushing down on the door. So it doesn't. It doesn't really. It just helps us visualize what's going on. If I said, like, the sled dogs push the sled at a rate of 15 meters per second, that would just screw people up. So I would say pull there. But consider the swimmer pushing off from the side of the pool in figure 4.9. You just imagine a swimmer going, here's the pool, somebody swims down to the end of the pool, there's the wall, they push off the wall and then they go back. That's right, they pull, they reach around from the other side, they pull themselves off the wall. With her feet, and accelerates in the direction opposite to that of her push. The wall has exerted an equal and opposite force back on the swimmer. So let's just say the swimmer pushes the wall with a force of 500 newtons, and the wall pushes the swimmer with a force of 500 newtons. Why does the swimmer accelerate? Don't these two forces cancel each other? If you add the forces up, you get 0. So how does the swimmer actually move?
Acceleration.
So are we thinking the Earth is big and the swimmer's small?
Yeah.
It's not that. It's something fundamentally simpler than that.
Oh no, they don't cancel each other out. They just go in the opposite directions. It's not like the net force cancels it out, but the forces are still going in that direction.
I think you're on the right track. So if we have the swimmer here, this is going to be a real bad picture of a swimmer. They don't look like they're swimming at all. But this is the swimmer, and I want to calculate the acceleration of the swimmer using F equals ma. So what do I put in for the net force acting on the swimmer? But don't they cancel out to 0?
No, but that's not acting on the swimmer. That's
Right. So that's the key. The force that's exerted on the swimmer is this one. That's the force of the wall pushing the swimmer. This force isn't accelerating the swimmer. That force is accelerating The wall. And the wall doesn't accelerate. That's where we get into, the mass of the swimmer is small, so the swimmer accelerates a lot. The mass of the wall is big. The wall doesn't accelerate much. The net force experienced by each of them is roughly the same size. But if we want to know how fast the swimmer's going, we just put in 500 newtons, and then we can calculate their acceleration based on that. So the answer, why don't they cancel each other out, is I'm just going to say only one force, only the wall's push is acting on the swimmer. And I'm going to leave it at that. I've already made such a mess here, I can't fit anything else in my mess. So you don't include them both. And we're going to be practicing with this idea. So the idea here is that the system in this question is just the swimmer. And we figure out all the forces acting on the system, and there's just one. Now, if the system were the entire Earth, including the swimmer and the wall, what would the net force exerted on the entire Earth be? 0. So the whole Earth wouldn't move. It's just that the little tiny bit of mass that is the swimmer, that part of the Earth's mass is going to accelerate to the left. And the rest of the Earth's mass is going to accelerate to the right, not very much. But overall, the Earth's not going to move at all. It's just going to it's just the mass in it is going to sort of change position. But if you just focus on what happens to the swimmer, there's only this one force, and the swimmer is going to go pretty fast. Rory? Okay. So Newton's third law examples. Please don't feel like you have to write everything I'm writing, because it's going to seem like it's too much to write. So how do you walk? And use Newton's third law as the context. So let's say we want to walk across the room to the left. How do I do that? I push the floor. Which way do I push the floor to walk to the left?
Behind you.
To the right. So, but for this I'm going to say, so the feet push the ground. Which way? I'll say backward. So not downward, because if you push them downward, then you jump. That's how you jump, not how you walk. So you push the ground backward, and then there's the ground pushing or pushes the feet forward. And this is a lot to write. Don't feel like you have to write, as long as you understand. If I say on a test, explain to me how a car drives northward. So how would a car drive northward? What would happen? What would you have to do? Well, how would the car accomplish this in terms of Newton's third law? What pushes what? What pushes the ground? The wheels. So the wheels, and I'm going to say wheels push the road. I'm assuming you're not off-roading. Southward. Doesn't always have to be southward, just in this example. And the road, therefore, pushes the wheels northward. So a little while ago I kind of mumbled to myself that the idea of action and reaction is a little iffy. So in these examples, can you pick out what the action is and what the reaction is? Or could you argue that either one is the action and either one is the reaction? Which one happens first? Do the feet push the ground backward first, or does the ground push the feet forward first? So your feet push backward and then the ground pushes the feet forward? How much time elapses between when one push happens and the other push happens? Like if I push the wall, or sorry, I need to do it so Samantha can see. If I push my desk like this, is there any time lag between when I push it and it pushes back? No. So from the standpoint of something happening and then something being the reaction to that and happening later, it doesn't really make sense. It's sort of a philosophical thing. I mean, we make the decision. I think, I'm going to walk. And then soon after that, my feet push the ground backward. and at the same time, the ground pushes me forward. So you could put these in any order you want, is what I'm saying. It doesn't matter. So it's not really action and reaction. It's just opposite forces. Helicopter, what pushes what? The blades. And which way do they push the air? Push, air, down. Or downward. And the air pushes blades upward. And then there are rockets. Rockets confuse people. When I first saw water rockets, I thought, oh, how does that work? But even real rockets, what do people think? Like if we were to continue here and I were to just question a whole bunch of people on the street, with a rocket, what pushes what? How does a rocket go? The fuel pushes the rocket? The burning stuff pushes the rocket? The exhaust pushes the rocket? So that's the actual reality. What's the misconception? What do people think pushes what do people think the rocket pushes? Most people would say, see, you're all just too smart. You can't relate to the common person. So the misconception is that a rocket is like a helicopter or an airplane, and that rockets push air. That's what people think.
Well, how would you fly in space?
I know, exactly, I know. So rockets, people do think this. I'm not making this up. This is yeah. Okay, in reality, rockets push exhaust backward. So the exhaust pushes the rockets forward. And now, as unbelievable as it is to you that some people don't believe that, if you had to prove to somebody that rockets don't push air, what would you say, Oscar? No, I mean, like my desk has no wings.
Okay, but it doesn't push air.
They go in space. There's no air in space.
Okay, there's no air in space.
Yeah. Okay. Rockets can accelerate in space. Rockets can accelerate in the vacuum of space. I'm just going to say can accelerate. Yes.
I mean, some
Does a hairdryer have wings?
In there it does, doesn't it? How does it push air? Doesn't it have wings?
Wings?
Little wings.
Does my mouth have wings?
Your lungs are kind of wings.
You have a very broad definition of wings. In outer space. Nothing can push air without wings. Yeah, normal. They have blades. They're little wings. Flies have wings. Normal. The fire. So if you've seen Wallace and Gromit, I can't remember if fire flew from their rocket, but if you see a rocket like this and you see this, all that stuff coming out, that's going this way. The rocket's pushing it out, and that's pushing the rocket up. And even though this doesn't seem like it has much mass, it comes out really fast, and a lot of it comes out.
Well, if those are equal, then how does that counteract gravity?
So here's this would be, okay, so let me draw these three. This is a very good question.
Wait, isn't that the same as this?
Yes, this is the swimmer thing.
Oh, okay.
So this is the force of the rocket on the exhaust, and this is the force of the exhaust on the rocket. And so that's the one. This is the one that gets named thrust. And so if the thrust is this big, the weight has to be smaller. So there's mg. So as long as the vector representing the weight, and we've got another one too we'll add on. There's drag too. So if these two add up to less than that, then the rocket can keep accelerating upward. All right, last couple of things to stick in here. We're skipping over friction for now. I feel like in the homework somewhere there's something about tension. And I have a really annoying definition of tension, but if I give you a simple one, I'll just be kicking myself and saying, they're going to think I didn't know that. So here's my definition. I'll read it first. The action-reaction pair of pulling forces, that's going to start a fight, of pulling forces acting at each end of a stretched object. And there are 2 asterisks in there. So this is page 8. The action-reaction pair of pulling forces acting at each end, and that's where my first asterisk comes up. In the other class, we had a lively debate about how many lines an asterisk has in it. Some people's computer keyboards had 5, and some people had 6, if you count all the little segments there. Yeah, I don't know. Mine on my computer keyboard is this. It's that. Yeah, some were saying they just had different numbers. So, forces each end of a stretched, another asterisk here, object. I like asterisk pluses, extra strong, heavy duty asterisks. So what this means is if we've got a tug of war going on, for example, and we have a string here or a rope, and we'll get to the fact that the rope has to be massless in just about all situations for physics to work. So one end of it is here and one end of it is here. So the person pulls this way on the string, but then the string pulls this way, and that is the force of tension. But at the other end, the person's pulling this way on the string, and the string's pulling this way, and that's the tension. So that's the action and reaction pair at either end of the string, and they're on one side of a person pulling away from the person, which kind of is the definition of pull. If you're on one side of a person going toward the person, then that's sort of a push. So I would call these a pull and stand by it. And now the asterisk is this. Is there any tension right here? Yeah. So right, it's everywhere in the string. So it's not just at each end. We're going to be drawing it at that because it would be ridiculous to draw all the tensions that you could possibly draw. There'd be an infinite number. So if you thought about what's happening to this point, this end of the string is pulling that way, and this end of the string is pulling this way with the same tension. And right here, this part of the string's pulling this way, and this part of the string's pulling this way. And if you add them all up, what's the net force on the string? 0. So all the internal forces are 0, plus this person and this person, they're pulling with the same force too. So the net force on this string is 0. Oh yeah. Okay, I don't want to get into that too far. Now, I said it's stretched. So what I mean is, it's tight. There's some pull there. It doesn't have to be stretchy though. It could be Kevlar. Kevlar doesn't stretch much. Could be a rubber band, which does stretch a lot, but it's just something that's taut. Now, this next part in our physics problems, almost all ropes, chains, wires, cables, strings will be massless. And it's because of this. If you have a chain like this, and you measure the tension in the chain pulling there, and the tension in the chain pulling there, where's it going to be stronger? The bottom or the top? The top, because it's going to have all this weight hanging on it. So the farther down you get, like this link doesn't have anything hanging from it, but right here it's got 2 links hanging from it. This has 3. So if these really had mass that we had to include, that would just really screw up our physics problems. So they're going to be massless, and okay. So and also the force of tension at every point is equal. And I don't want to get into why, but Newton's third law is what you would use if you wanted to try to prove this. But I don't have time to try to prove that. So that's all you really need to know to do the homework. The homework is, yeah, it's 4 problems on page 14. So it was 1 through 4 on page 16, and this is 1 through 4 on page 14. We're just going to do the first 4 problems.